This is Momentum of Collisions pre-lab, and the idea is that there's a lab that we can do, or at least we're going to do virtually, where two objects collide, and we can figure out the momentum, and we can do this without actually calculating velocity. And so I'm going to show you the setup for this lab, and we're going to tilt a little bit here so that we can see this better. Okay. The general idea is that you're going to, or at least when we're in class, that there's a table, and on the table then we have a ramp of sorts, and so I'm going to draw this, and we should probably zoom in a little bit more, okay? But the idea is that there's a blue ramp that we've used, okay, and it's shaped like this, okay? And off the edge of that is a small metal hook, okay? And with this hook we have a little set screw, and it just holds a target ball right there, okay? And we're going to have a very specific leaving point here. Now I'm going to make this one solid, and then the other one's going to be hollow, okay? And they're arranged in such, well, let me show you this. Then we have a string that comes down, a plumb, right? And so that shows us exactly where the collision takes place. Now what I want to do is show you what this actually looks like from above, okay? Because they are what we call offset. And what that means is that the incoming sphere, the incident sphere here, the incident sphere is going on its straight path, so we can draw this like that, okay? But it's in such a way that when it collides with the target sphere, right, that they collide at an angle. So this is what it would look like from the top view, right? In other words, that happens right here where that string shows that there's a plumb bob going straight down, okay? So what happens is after the reaction, after the collision, one ball goes off in this direction and the other one goes off in its direction, okay? And so we can actually measure that on the surface of the floor, okay? So let's go back to our table and string drawing here. What we're actually going to have is on the floor is some carbon paper, and you've used this before for the marble launch. And so what happens is now we should probably make sure we extend this to the position of collision here, okay? I want to show you now what that would look like. So when we're on the floor, we actually have carbon papers on top, and we'll have 4 sheets of paper, so I'll just designate them something like this, right? And we need a big sheet of paper because the collision causes the spheres to come pretty far apart. What we can do then is designate this target, or this collision point right here. In other words, that's where the collision took place in the air. And this plumb bob, I'm going to designate that down here. That plumb bob is positioned right there above the paper. So this little star here, right, is indicated on this set of papers here. So we removed the carbon paper here. And what happens is after the reaction, or after the collision rather, we have a bunch of dots. And so I'm going to show you what happens here, and then I'm going to give you some lab data here. The first thing you have to do in trial 1 is you have to roll the incident sphere all by itself, okay? And the reason is because this single ball, this alone incident ball, provides all of the momentum for the collision. If you think about it, this target here has no momentum because it's obviously at rest. So m1 v1 or m2 v2, mass times velocity, he has no momentum because there's no velocity. So what we do is we run that incident ball all by itself several times. Now we really hope that we get a cluster better than this one. Okay? In a lab situation, it is ideal that we should get a cluster that is maybe no bigger than a quarter, for example, right? The area of a quarter, or maybe even a $50 size, a bigger coin. And so we hope to get that. Okay? What you then do is you look at these cluster of points and you decide which best represents the distance from the collision point to those spheres. And we'll talk more about that because I'm going to give you data in a minute, okay, or at least in Google Classroom. But if you remember now, we had the target sphere, and what happens is now after the collision we have the target sphere, and we're going to draw this as this. Now obviously they don't show up as hollow dots, they just show up as impact points. But let's say that after the collision, right, the target sphere ended up over here, and we did several collisions, right? So trial 2 is now going to be incident sphere and target sphere. So here's the target, or incident sphere, and then this is the target, okay? And the concept works like this, that this alone arrow, right, we can now draw a vector, right? We can draw a vector there. And that vector actually represents the velocity. So this here is the momentum vector. And that shows us the momentum of the incident sphere, and by virtue that is actually your m1 v1. Okay? And we can do that because if the masses are the same, then we don't have to worry about mass. We can factor that out later on. So it does work. It seems a little weird, but that's our momentum vector. Then what we can do is we have the collision, and we can go from the collision site up to the target area. So now we have a target vector, and we color that as orange. And then you can do the same thing with here. In other words, you get to choose, and I can give you lab data on Google Classroom. This takes about 20 minutes to half an hour in lab to do. But the idea is that when you are done, you now are going to transfer all of this, and these are very large, by the way. You're going to transfer this to a single sheet of paper, so you're going to have to scale it down. Okay, so this might be as much as 30 centimeters, and this might be 43 centimeters or something like that. And I'll show you more in the post-lab paper or the pre-lab paper. Okay, but now we're dealing with an 8.5 by 11. Right, that's just a standard copy sheet of paper. Okay, so we've transferred everything now, and we can still draw this if we need to, although it will be a point. It won't be this big blob. Okay, and we measure now using a protractor and obviously a ruler, and you really need to measure to at least 0.10 centimeters, right? You have to be really specific on this one. And so when we measure this, right, we now have to have the angle. So we're going to have to go back to our imaginary drawing, or our drawing that I provide for you in the lab data for this. Okay. So we could measure this, for example, and say that that is about 63.1 degrees. Okay. So then we again place this here. And the idea is that you have done this kind of thing before, and that is when you do the vector sum of the incident plus the target, right? The vector sum of those should come to equal the incident sphere alone, right? So by doing the head to tail method, we could draw this, right? This is also your incident sphere. And so then we could, in a sense, cross that out. And now you would have this new vector, and I'm going to draw that in pink. I'm sorry, we should probably draw that in an alternate color. So we're going to draw that as a dashed arrow, right? You need to do that because that's a resultant. Okay, so we can call that R. And so that resultant there is what gets compared to this original incident sphere. Okay, so we should probably scale that up, and I'll do that in the lab data. But the general idea is that you're going to compare the vector, the momentum vector for I, and I guess we could draw it like that. You're going to compare the momentum vector for I to the momentum vector for R, and the question is, are they equal? And they might be. That happens, and sometimes we get very precise results. But we want to look at how they are equal in two ways, and one is the length, which represents the magnitude, right, the size, the magnitude of the momentum. But we also want to do that in direction, and that's going to be angle, right? And so generally what we will do is the difference of the angle. In other words, is it off by 1 degree or off by 2 degrees? With length, we do, we can just do centimeters. We don't have to do kilogram meters per second in the units of momentum. Now, that's the simple version. Okay, and I want to show you another situation though, because there's another trial that goes on here. And this time we're going to take the same situation, okay? But this time we're going to have a larger incident sphere, okay? This larger incident sphere here for trial 2, we're going to say that that has a 28.1 gram incident sphere. So when that guy comes in, that's going to strike the target. And then we're going to leave the other, we can call it 8.4 grams for the target. Okay? And again, we would do the same situation. Let's call that 8.41 so that little dot's not just hanging out there by his own. Okay? And we could call this 2.811. Okay? So we would measure these on the electronic scale, and we would get these values here. We do have some adjustments we need to make in that situation. Okay, so again, I want to show you now what would happen if we carry out the same collision. So this time we have a larger sphere up here, and we could draw that in if we wanted to, because we are going to get a different situation. So now it's still offset, right? We are still offset here, larger here. But now the way they move is different. And we can still do this, but I want to show you the different set of results. Now, we can, in fact, draw the 4 sets of paper, right? 4 sheets here. Okay. Let's draw it so that we have this on top now, right? That's where the collision takes place in the air directly above the sheets of paper. And what you do is you run the alone ball, right, the large one, and we'll represent it like this, but usually it's just dots. And sometimes you get one of the guys that comes out here, okay? But you choose, you decide which one best represents the cluster, okay? So we'll just draw this, all right? So somewhere in there we could say that is a 14.3 centimeters or something like that, okay? Then we carry out the collision, right? And the target here, or the incident rather, ends up in this area. So we get as many as 8 to 10. But what happens now is that the target sphere goes flying off in this really far direction. Okay? Really far. And then you might be tempted to say, well, wait a minute, that I can tell you right now, if I add those vectors, let's go back to this one, where we had incident sphere in blue and target sphere in orange. Let's take the target. We'll draw that one in orange. Okay? And then the other one was blue, so we'll draw that here. Okay? You know pretty quickly that orange and blue are not in any way going to come together and equal the pink. There's no way that that vector situation would happen. So let's say that we scale it down again. So we scale this down, and that won't be a problem for you. So if this is, for example, 14 centimeters, right, and this is 22, there's no way it's going to fit on a regular sheet of paper. That will not be a barrier for you. So now we are on the 8.5 by 11. Okay, so we are on a regular sheet of paper, and you redraw everything. So we can draw from the top now. Well, let's talk about this guy right here. This incident vector actually has to be corrected. It has to be adjusted, if you will. Okay, because the masses up here are not the same. The masses are very different. And so what we have to do is correct that vector. We have what's called a vector correction. And we have to basically scale that vector to reflect those masses. But it's actually very easy. What you do is you simply put the ratio of the small to big. Okay? So when you put the small mass relative to the large mass, by doing that ratio, that helps you correct that vector. And so here we would have something like 8.4 over 28.11 becomes 4 over 14, 2 over 7. So it becomes about 0.28 multiplier. Okay? So what you will do is you will multiply your orange vector up here, right? Let's say that's at 24 centimeters, right? So you would take the 0.28, multiply by the 24 centimeters, let's say that is 24 centimeters, okay? And this is less than 1/3, so we're less than 1/3 of that would be put us at about a 7.11 or something like that. Let's just call it 7.11 centimeters, okay? That is now your corrected vector. That is what you will add to this incident here. Or this, yes, this is the incident sphere that went away, off to the right, if you will. Okay? So when you're done now, you will take this vector here, that's your incident from, okay, this incident here was here, but now this orange one got corrected, right, and became this green one. And when you add them together, we can take that green one there, act like we crossed that guy out, excuse me, draw this resultant vector here, and then we can compare it to the pink. Okay? And hopefully it goes close. But you get the idea is that now we can again talk about the direction and the magnitude. Right? We can talk about those two things. So let's back up a little bit, make sure that you're ready, so when we give you the lab data that you'll know what's going on. The situation is that you have a ramp that has two equal spheres. This one's drawn bigger than we had in the original. This incident sphere strikes this target. The collision is drawn precisely or specifically above a landing pad here with carbon paper. And when we are finished with the collision, we find that the incident went off to the one side and the target went off to the other side. But all of the momentum actually comes from the incident sphere, so we roll that one alone. And the idea is that if you take the momentum of the incident sphere after the collision and the momentum of the target sphere after the collision, these two should add up. These two should add up a vector sum to equal this pink one. Okay? So what we do then is we transfer this to paper, scale it, we tell the reader what the scale is, and when we add them, we now have a resultant vector of adding those two, and we add it to the incident alone. Okay? We'll need a ruler and protractor to do that. But in another situation, we have the target and the incident sphere are not the same mass, so we have to make a correction here. And we do that by making a ratio right there. Okay? So in Google Classroom, we will have a set of data for you and probably some more explanations and a lab data sheet.